Okay. Uh, so I think you are able to see this, right? So a question, if it's asked, what is Zener diode? I think many of you know what's a Zener diode, isn't it? Have you used in your labs yet Zener diode, or have you started learning in your theories? Anybody, what's a Zener diode? Have you heard of the term Zener diode? I think basic electronics should have studied,
Yes.
right? Okay. So this is used basically in the reverse conduction, right? Okay. And we'll just go through it. The regulated power supply may use Zener diode as voltage controlling device. Okay. The output voltage is determined by the reverse breakdown. Okay. So this is important here. Okay. The reverse breakdown voltage of Zener diode. Now this is the property in which we are exploring Zener diode. So we are taking something called the breakdown of the voltage, but in reverse direction. Okay, usually we use diodes in forward conduction, right? And we bias it. Okay, we do a positive bias, and then we utilize the components. But then here we are trying to make use of Zener diode in its reverse breakdown. Okay, in reverse breakdown mode. This is nearly constant for wide range of currents. So that's the reason, we pick up Zener diode. The load voltage can be maintained constant by controlling the current through Zener diode. So as you can see here, this is an unregulated power supply. Can someone tell me what's an unregulated power supply? We have discussed this, right, in our previous session. What is unregulated power supply?
Sir, it which gives a constant power throughout the time.
Unregulated.
So it's not stable.
It's not stable. Okay. So Cyan, the one that you told was, opposite. So the one which comes, which has a lot of spikes and which has lots of ups and downs, and it's not at all stable ultimately, right? So those kind of power supplies are generally referred to as unregulated, which means it's just a power supply. That's it. Okay. So we have a resistor here, and then we have the current I1, okay, which is passing through the resistor R. Now, if we can control the current that is passing through the Zener diode, okay, then ultimately we can make sure that it becomes constant. Okay, so we are exploring the properties of this Zener diode. Okay, and using the current that passes through Zener diode, okay, we can make sure that the voltages are also constant. So how do I make sure that this currents are constant? Okay, so basically we should give a range of voltage. Now, as you all know, voltages are nothing but potential differences, right? The potential difference between one point and another point. That is why you have positive and negative, right? Or sometimes you give supply with respect to ground. Okay, this is because to create a potential difference. So once the potential difference is created, it's then on your electrons will start moving in the opposite way, right? So you can find that once the difference between these potentials are higher, okay, then what's going to happen? You can find that the amount of current that passes through also becomes high. So if you want to reduce the current, then the voltages also are to be reduced. So this is one best advantage of having a Zener diode. So ultimately you can see that the current I1 and I2, okay, how they are related with IZ. IZ is nothing but your Zener current. So I1 is equal to I2 plus IZ, because this is the current that passes through here, right? Okay. The Zener diode has limitations of range. So that is one disadvantage. We cannot use it for, an unlimited range. Every device has its own shortcomings. So does Zener diode. The load current range for which regulation is maintained is the difference between maximum allowable Zener current and minimum current required for the Zener to operate, right? So what do we understand by this? We understand that there is a minimum potential or minimum current that is needed for the Zener to operate. I cannot just say, okay, 0.001, okay, volts, you start operating, which is going to be too minute, right? Neither can I give too high voltages and say, yes, come on, start working. No, that is not at all possible, right? So it has a certain range of frequencies that it can operate. It has a certain amount of voltages that it can operate. So those has to be kept in mind, and only in that band of safe operating region is what we are going to utilize the services of Zener diode. Okay, so any device for that matter, okay, it can be diodes, it can be any electronic equipment. See, whenever you buy an electronic equipment, okay, there will be specifications there, right? Maximum frequency 50 hertz, right? 50 to 60 hertz, and the maximum voltage that it can take is about 220 to 250 volts, right? So if you connect it to a 1,000-volt transformer, then you cannot expect your electronic device to perform the same way that it was designed to, right? So ultimately, we need to go through the specifications and extract the best from any device. Now let's take a small example here. If Zener diode requires a minimum current of about 10 millivolts, okay, and is limited to a maximum of 1 amps, okay, so we are having a range of 10 milliamps to 1 amp. The range is 1 minus 0.01. So this is going to be the range. So I am minusing 1 amp with 10 milliamps. Okay, so which means the operating range that it can work on is about 0.99 amps. So if the load current variation exceeds this amount, okay, then the regulation may be lost. So here we are using this Zener diode as a regulator, okay, as a controller. Regulators are normally used to control the current, right? You can take the example of the fan, right? So it has a regulator, and as you increase the regulator speed, okay, so does the rotation of your fan change. So this is nothing but allowing more current, allowing less current, and making the motor run, right? Any doubts with this concept, students? Is it all fine with the Zener diode?
Yes.
Yeah. Okay. So Zener diode has its own range of operating frequencies, has its own range of voltages and currents. So here we are extracting its property of reverse breakdown. Okay, reverse breakdown, and due to which we are exploiting its property. Okay, fine. So next, how can we use this power transistor as emitter follower? Okay, so power transistor, how can it be used as just a question if it's asked? Okay, then how you can answer. Of course, they are not going to tell you to draw a circuit and explain it, but just for the purpose of understanding, okay, you should be knowing. Now, if you see here, okay, uh, this is this is your transformer here, okay, which is capable of 110 volts and 50 hertz. As I mentioned previously, okay, you have step up transformers, you have step down transformers, right? And then you have this diodes and transformer turns connected to ground, right? And you even have, see, whenever you have this kind of symbol, okay, it's nothing but a Zener diode. Okay, then you have a capacitor, You have load at the capacitor, the current at the load, resistance at the load, and the final output voltage. So here, we are looking at a transistor. Okay, so we are looking at a transistor, and that transistor is referred to as power transistor. So it has a base, it has an emitter, and it has a collector, right? So I think all of you are very much learning these in linear integrated circuits, isn't it? So this becomes your base, and this becomes your emitter, and this becomes your collector. So we are looking at a transistor here. Okay, fine. To obtain better voltage regulation in shunt regulator, shunt means parallel, in parallel regulator, the Zener diode can be connected to the base circuit of power transistor. So you can find that a Zener diode is connected here. Okay, and we are again exploiting, or we are utilizing the property of Zener diode. Now, we all know that VBE, okay, voltage across the base and the emitter, plays a very important role in driving this transistor. Okay, so which means what we should understand is, if the potential or if the voltage is given at the base is higher, okay, then this transistor turns on. If not, if it's too less, okay, if VB is too less, then we are sure that this transistor wouldn't turn on, right? So with the help of the Zener diode, we are trying to control, okay, this current that is passing through the transistor. To obtain better voltage regulation, the Zener diode can be connected to the base circuit of a transistor. This amplifies the Zener current range. It is also known as emitter follower configuration. Now, the reason why we call it emitter follower is because whatever is there, okay, whatever outputs that you're getting here, okay, is actually at the input side. So input side, whatever voltages are there, whatever currents are there, the same thing you obtain at the output side. So hence it is called emitter follower. Okay. This configuration reduces the current flow in the diode. Okay, so because of this configuration, what is going to happen? There is going to be a reduced current flow. So if there is a reduced current flow, then the range of operation of this Zener diode is also going to be reduced. So if it is reduced, then ultimately current is also reduced in Zener diode. So if the currents are reduced, then obviously we should understand that it has been able to successfully reduce the voltages, because currents are because of voltages, right? Okay. The power transistor used in this configuration is known as pass transistor. The purpose of, okay, CL, that is this transistor here, is to ensure that variations in one of the regulated power supply loads will not be fed to the other load. So whatever variations are here, okay, it is like a shock absorber. Okay, so it can take up those variations, because ultimately this capacitor charges and discharges, so it will store all those changes. Okay, and then we can extract it across the load. So the capacitor effectively shorts out high frequency variations. So any high frequency variations can be nullified, can be cut off with the help of this capacitor, which is here. Okay, because of current amplifying property of the transistor, okay, this transistor that we are talking about, the current in the Zener diode is small. Okay, hence there is little voltage drop across the diode resistance, and Zener approximates an ideal constant voltage source. So as I mentioned previously, if the currents are less, it means the voltages are less, and we have connected it in the reverse bias, and we are exploring the options of its reverse breakdown. So this capacitor here, it works like absorbing high frequencies, because Ultimately, we are looking at the charge and discharge cycles of capacitor, and at the load, okay, parallelly it can be taken out, right? So can we move on to the next concept, students? Yes.
Yes, sir.
Okay, thank you. So we have seen the circuit, the operation of series regulator circuit, okay, using Zener diode, and how a power transistor as an emitter follower along with Zener diode, how it can help us in controlling the currents. Now, I think you must be aware of the concept of optical fibers. Are you all aware of the concept of optical fibers? Where have you seen them?
Sir, is it for the broadband connection?
Very good, very good. So these days, we see this optical fibers, the one um, which looks like a glass, flexible glass, the fiber, right? So that is called an optical fiber. So basically the concept used there is the transmission happens with the help of light. Okay. So do you think light can travel in uh, a bent path, which means if it's right angled, can the light pass through?
No, sir.
No, it cannot pass, right? Light passes through only through straight or probably minimal curves, right? So this concept is very much used in optical fibers. So it has core cladding and jacket. I don't know if I've put it up here. So the center part, of the fiber is called the core, okay, and then you have a small layer on top of it, so that is called the cladding, and the outer part, the plastic, the fiber part is called the jacket. Okay, so these are the this is the cross section of optical fiber. Fine. So there can be a problem based on reflection, refraction. uh, okay, so I've just put it up. Okay, can someone tell me what is the difference between reflection and refraction? We have seen this in our preliminary or basic sciences.
So refraction is bending away of light to another medium, and reflection is reflecting the light which gets back on the object.
Correct, very good. So if in case you try to put a stick, okay, small stick in a water body, you can find that some portion of the stick you find it to be bent. Okay, so that can be referred to as refraction. Okay, and reflection, as we all know, the light which hits and just gets back is called reflection. Okay, so there are few concepts, okay, where you need to learn about the angle of incidence, okay, refraction and Snell's law. In physics, you would have seen this, right? Snell's law. So, so he says that n1 sine theta 1 is equal to n2 sine theta 2. Okay, so this is the angle referring to n1, and theta 2 is referring to n2. So in the question, okay, we have a monochromatic light ray, okay, which passes from air. Generally, we take it as n is equal to 1, and from air, okay, the light passes through glass, and it has about 1.5. That is the angle of incidence, okay, at an angle of 30° with respect to the normal. Normal means it is taking 90° into consideration. Okay. What is the approximate angle of refraction? So we are saying that we have a light ray passing from air medium and that light ray is getting into a glass, okay, and the refractive indexes are given for them for air and for glass at an angle of about 30 degrees. So what is the angle of diffraction? Right. So we will have to make use of the help of Snell's law here. Okay, n1 sine theta 1 is equal to n2 sine theta 2. So you will be needing this if in case you are planning to get into communications, right, in the field of communications, wherein these days, you can see it yourself, these days most of the broadband connections are all, with respect to optics, with respect to optical fibers. Anywhere that you see high speed data transmissions, okay, once you graduate and probably plan to get into the field of communications, then yeah, this particular concept is going to be very much helpful for you all. Right, so we take it as 1 and then sine, then theta 1. Okay, theta 1, we know that it is about 30 degrees, and then n2 is 1.5, and we need to find out what is this theta 2. Right, so we can make use of the inverse property. Okay, so 1 into sine 30, I get this value divided by 1.5. This 1.5 comes down, so I'm left with only sine theta 2. So if I want to find out theta 2, then I take a sine inverse of this value, which is 0.33, and I should be getting about 19.47 degrees. So this is going to be the angle. Okay, so as the light enters a denser medium, it bends towards the normal. So you can see that, with this indexes given, see, air has 1 and glass is about 1.5. So it is entering into a more dense medium, okay, which means it is not as free air, right? So as the light passes through a denser medium, okay, so there can be bending. So that bending is happening at a degree of 19.47. Is this clear, students, with this concept that we looked into? Yes. In physics, I think you would have studied this, isn't it?
Yes, sir.
Yeah. Okay. Fine. So there are two types of losses. Okay, I'll just quickly probably get into it, and yeah. So there are two kinds of losses that can be seen here with respect to optic fibers. Number one is the ray-like scattering, and number two is the micro bend. So as I mentioned previously, these micro bends can happen in optical fibers, and due to these bends, what can happen, because we are dealing with light passing through in the optical fiber, right? So because of which, due to some bends, there can be loss of this data. So data here is in the form of opticals, so which means in the form of optics, which means in the form of light, right? So whenever there is a bend of these uh, optical fibers, so you can see that there is loss of data. Then there is something called scattering. Okay, now due to the light scattering also, there can be loss of data. So we'll just look into this, what it is telling us about. The scattering loss is due to the non-uniformity of the refractive index inside the core of the fiber. Now, as you all know, once the light passes through, it has to, reflect. Okay, the light reflects and then comes out. Okay, so you can see that here, yeah, I mentioned it here. So this is the, type of reflection that happens inside internally. Okay, so the light passes through, it hits, comes back, it hits, comes back, and then it exits the fiber, right? So internally, this is what happens. So if in case there is no proper there is no proper reflection of light that happens, then there can be a lot of scattering. So this can happen because of the non-uniformity. So maintaining a proper refractive index is important. Now, as I mentioned, what is refractive index? The property of, or something which helps the light to pass through. Air has 1.1, and we saw in the previous example glass had 1.5. So the index has changed. So if the index has changed, the way in which light propagates through the optic fiber also does change. So because of which, okay, there can be loss, and that loss is nothing but called Rayleigh scattering. Okay, so there can be a fluctuation in the order of these scales, and because of which we have Rayleigh scattering. Micro bends, as I mentioned, these micro bends are because of the small damages that can happen, the small bending of fibers. So these are some of the reasons as to why there can be loss of information while using optical fibers. So we will look into this in our upcoming classes, and we will see as to what can be done to get this rectified. Okay.